Oh, hello everyone. My name is Ricky Telg. I'm the director for the Center for Public Issues Education and Agriculture and Natural Resources, which is part of the outreach core for the Southeastern Coastal Center for Agricultural Health and Safety. And it's my pleasure to welcome you all to a webinar, as you can see there on your screen, that focuses on wearables and exoskeletons. The title is Agriculture Ergonomic and Biomechanics Research with Dr. Jay Kim from Texas A&M University. I'll introduce him in just a moment. Again, thank you for joining us today for this webinar that should take about an hour or less. Our process here on our webinar series is that if you have a question or a comment for Dr. Kim, please place that in the Q&A on the Zoom screen that you're watching this on. For almost all of us, it will be at the bottom of the screen. So please feel free to put your question or comment for Dr. Kim in there at any time. I will facilitate the discussion and Q&A at the very end of his presentation. So if you have a question and you don't want to forget about it, go ahead and put it in there, and we will get to that at the very end of the presentation. We'll also have a very short evaluation. I'll put the link in and share that with you at some point during the presentation today. We'll also have that on the very end slide for today's webinar. So today, as I mentioned, we have with us Dr. Jay Kim. He is an associate professor of environmental and occupational health at Texas A&M University. His major research interests are in occupational ergonomics and biomechanics. He is particularly interested in developing and evaluating evidence-based interventions to reduce physical exposures, to reduce occupational injuries and illness, and therefore improve workers' health and well-being. And with that, I would just want to go ahead and turn it over to Dr. Kim. Thank you so much, Jay, for being with us today.
Sure. Thank you so much for the nice introduction, Ricky. And it's really honored and a pleasure to be here today. And I would like to showcase some of our research in occupational ergonomics by mechanics that's particularly linked to the agriculture, commercial fishing, and forestry. And much of the work have been supported by various so collaborators and the sponsors. So I'd like to first acknowledge those are the collaborators and my students and postdocs, who made this work possible. And also, I'd like to reiterate that what I'm presenting today is really my responsibilities, and as well as my collaborators. It does not necessarily represent any official view of those sponsors. So, I'm not going to go into much details about the injury statistics or, important statements on agriculture, injuries and, health and safety and health. But, why the ergonomics and biomechanics is particularly important in agriculture is, as we all know, that agriculture is still considered as one of the most dangerous industries in the United States, just due to high incident rates as well as a severity of the work-related injuries and illnesses. And among those, musculoskeletal disorders actually account for the single largest component of all work-related injuries among the workers, ranging anywhere between 40 to 60%, depending upon how we define those. And the key risk factors are all related to ergonomic risk factors. So I think that's why ergonomics and biomechanics is really important in agriculture and industries. And also, I do see some challenges that we are facing in the work population, especially in agriculture. And if this is sort of interactive sessions, I would have asked you the questions, but I think I will just present what the most, the important challenges that we are facing in agriculture in terms of work populations, as well as the environmental factors. The first one would be the aging workforces. I think this is happening across all the board in any industries, but aging is creating various challenges because aging is associated with the numerical adverse health outcomes, but that's at the same time, if you stay in the workplaces for the longer or later in your life, two major things we are facing. The first, as you all know, as we get aged, we lose our physical strength and capabilities. At the same time, and the longer we work in, similar or different industries, the total cumulative exposure to various work-related hazards are increasing, right? So therefore, it is likely for us to develop work-related injuries and illnesses. So this is showing very beautiful bell-shaped, age distribution back in the 50s. And when we say like aging workforce, depending upon where we define and then area, so we usually, define those aging workforces for the age of either 60 or 65 and older. So like this red line, the crossbar is representing that, the age of 60s. So please try to compare what's happening above this red line and below the red line as time goes. And this is just, every 5-year increment to showing how this age distribution changes, over time. So, this is 2010 and 2015, and this is about where we are now, and this is what is being projected by the 2050. So, if we compare this to what we have, the back in 1950, so we have a dramatic, changes in the shape and the of these age distributions. So as you can see, right now or going forward, we have a lot greater proportion of those aging population as compared to the younger populations. So this creates, the not unique challenges, but it challenges in the agriculture workforces. And another one is becoming more major in mainstream these days, heat stress due to the climate changes of global warming. So this particular map showing the heat map that compared to the 20th century average in the United States. Basically, darker, anything in blue representing that this particular region of the country show, at that time of, that the average temperature was cooler as compared to the 20th century average for this. And then anything in red showing that the temperature in this region was hotter than the 20th century average. So to look at how this map changes as time goes. So basically, we are losing these blue regions, and now, by the time now this is up to 2020, so there's no single states has a average temperature cooler than the 20th century average. This is really particularly concerning in agriculture where a lot of people work outdoors. So, and another one is obesity, and obesity, is associated with various adverse health outcomes. But at the same time, it comes, when we talk about PPEs and some other, to control safety measures, and obesity creates a lot of the challenges in terms of fitting those and in terms of safety margins and limits of those PPEs and safety the equipment. So this back in the days, obesity was not actually of our concern. Therefore, a lot of states here, represented by the white colors here, and they didn't have data about obesity. And some states have the data on it, but still most of those states were obesity rate has less than 10 to 14%. So major part of the country were relatively healthy and lighter as compared to now. But look at this map changes as time goes, and this is from the 1990s. And as you can see, as time goes, we start to fill all these white places. Now we have a lot of darker blue states, and where obesity rate is somewhere between 15 and 20%. But this is just only the beginning. As time goes, we started to have new categories starting from 1997. We have the new 3 states have obesity rates greater than 20%. And we started to have a lot more yellowish area, and then now started to see the orange color, which has had obesity rate greater than 25%, around the 2000. But we started to fill those states with these orange colors. In 2005, we had another category of the obesity states that has greater than 30% of the obesity rates. And the story goes on, by 2010, we lost all the blue states and now everything is in red. And now, 2011, and the CDC thought that, so this is not going to be informative because, every single state is going to be all, blackish, dark red. So they redefine this, what obesity is. So, if we look at this map after 2021, I mean 2011, we cannot compare this map to the previous years because they redefined what obesity is. So, but now that we are back in the states where we have a little bit, greenish colors, but this didn't help. But as time goes, we started to have a lot more reddish color again. We start to lose all those greenish colors. And this is where we are today. So basically, this is very different from what we have seen, back in the days. So if we compare these, cross-sectional comparisons by 5 different time points, in terms of the obesity rate is very different. So those are things are really creating, heat stress and aging and obesity actually, to put us in the really great danger in terms of increase the risks for the adverse health outcomes, particularly among those agricultural workers. And also, those are environmental factors and individual the factors coming from the people. But at the same time, in these days, various technological developments, we have seen robotics and AI, machine learning. With AI is not a new thing. Robotics are not a new thing. We had this for almost like several decades. But why AI and robotics is becoming more prevalent is drawing the public attention across the domain is the computational powers. We knew that there is machine learning. We knew that AI is concept existed for so long, but we haven't had such a great computing power to realize this. So now, since we have sufficient computing power, which will be ever increasing over time, and this open up new challenges and at the same time opportunities. And then we, for the next of several slides, I will be showing how we have been using and incorporating this AI, machine learning, as well as wearable sensors to improve the worker safety and health in agriculture. So the first part of this talk will be related to wearables that we have used in the lab and field to evaluate the injury risks among the agriculture workers in the commercial fishing, forestry, and agriculture. So this was published recently, but we use the wearable sensors to characterize the musculoskeletal injury risks among the commercial craft fishermen. And as we know, a lot of commercial fishermen work offshores, which particularly make difficult for us to evaluate their injury risks, because we cannot be with them. So, but using the wearable sensors, we were able to objectively quantify and characterize those biomechanical risks using those, in offshore while they're performing this commercial fishing. So as I don't know if you know how heavy those, commercial, crab pot is, but basically the empty crab pot weighs anywhere between 80 to 100 pounds, which is very heavy. But that's not it. But it also needs the weights and baits that comes with so that this sink at the bottom of the ocean does not move around. So with the field craft, this particular Dungeness crab pot can weigh as heavy as like 400 to 500 pounds, which is very fatiguing. And they pull this crab pot anywhere between 200 to 1,000 a day. So this is very fatiguing. So traditionally, we have been using the video footage to just characterize what those musculoskeletal risks are, and also what would be their, prevalence of the injuries. However, using those wearable sensors, we can non-invasively evaluate what are the actual hazards associated with their low back and shoulder injuries, which are a lot of very prevalent. And using this data, we were able to actually, model the 3D biomechanical, develop a 3D biomechanical model to better understand what are actually the low back injury risks. Left column, I mean the right side graph showing lumbar compression and shear force that's, that we can measure using these wearable sensors, and then, compare that to the NIOSH maximum permissible limit or action limits. And as this red line represent on the slide, this is anything above the 200, 600, 6,400 compressive force of a lumbar spine. That's indicating anything above the 6,400 newtons, meaning that there is a substantially higher risks of getting the injury if this person is on this occupation for prolonged period of time. And also the ACGIH TLV also set the action limit, which is the 3,400 newtons. Which is also consistent with a NIOSH action limit. Anything below is a safe zone, and anything between 3,400 and 6,400 showing the caution. So as you can see, this good proportion of all those compressive force, and this box plot is showing the lowest portion of that bar representing 25th percentile compressive force, and the top part of this a the box plot showing the 75th percentile of a compressive force. So as you can see, all these compressive force were above this action limit of 3,400 newtons, 3,400 newtons, and good proportion of this compressive force exceeded the maximum permissible limit, which NIOSH recommend absolutely not exceed this value. Similar in the middle bar showing the shear force. And as you can see, in good portion of these bar, almost half, about, 40% of these, the measured, shear force exceeded the not ACGIH TLV value of 700 newtons. This is basically indicating how fatiguing, how stressed it is that commercial fishing task. So, based upon what we learned that this crab pot handling actually pose considerable or substantial, low back injury risks. However, fortunately, those brilliant group of fishermen develop a sort of engineering intervention, and not all the vessels use this, but we have identified several vessels have used this, something called banger bar. So banger bar is a sort of the structure you can see on the center of the screen, has a padding and the stop bar, so that the fisherman can actually flip and bang the crab pot against this bar, so that they can release the crab easily, and they don't have to go all the way down to the bottom of the table, which actually reduce those lumbar flexion. Therefore it can potentially reduce the low back strain. However, these fishermen didn't know, if it is really beneficial or not. And also some of the vessel owners and the fishermen didn't have these banger bar, wanted to know if there is any evidence-based suggestions or data, so that they can use to justify to install these. So we, thus funded by the NIOSH, we ran a lab-based studies where we could, simulate these crab by handling tasks to quantify objective biomechanical model, I mean measures, to come up with evidence-based recommendations. In this particular study, our objective was to evaluate the efficacy of this band bar in reducing musculoskeletal injury risk, particularly in the low back regions. And the pictures are shown on the slide are showing the actual professional, those fishermen who actually visited our lab during the COVID and helped us to set up the lab and the crab pots and all the settings that are realistic and representing the actual commercial fishing work. So our study design in our repeated measures study, lab-based studies, we recruited 25 healthy individuals and simulate these crab pot handlings to evaluate various different conditions with no Bangor bar as a control conditions and then four different Bangor bar conditions. I'm not going to go into too much details here, but this is what we have found. So, we using various bioinstrumentations, and I'm not going to go into details, but we just, this is showing how rigor our method was. So basically, this is just, the snapshot of what we found. And anything that you see from the darker, highest bar on the graph showing the no bar, which is control conditions, where, which is representing their conventional way of doing the crab pot handling. And lighter bar showing the Bangor bar conditions with a different setup. So, and then the lowest bar the bar was set up to high so that they don't have to bend their low back too much, so much. So as you can see, the this using the Bangor bar actually substantially reduced the low back stresses, and also this low back stress decreased as Bangor bar height increases. And this is showing the low back muscular loading. So basically, we used a electromyography, which is very similar to ECG that you can see in the health clinics. So we basically measure the most activities using surface electromyography to see using this will actually reduce a muscular load. And similar to what you've seen from that low back moment data, and using the Bama bar actually substantially reduced muscle activities more so on the right side of the low back extensors. But regardless of the left and right side, you can see this consistent decrease in the muscle activities with the Bangor bar use. And similar to what you've seen from the previous slide, these muscle activities also decrease as the Bangor bar height increases. And we also not only use those objective biomechanical measures, but also we wanted to see if these biomechanical measures, especially related changes, actually measured by their perception. So this is showing the perceived localized exertion, especially in low back regions. And as you can see, the trend was consistent, saying that Bangor bar use actually reduced their perceived exertion, and also this further decreased as the Bangor bar height increased. So like to summarize what we found there, this study found that crab pot handling posed substantial biomechanical load, but this could be reduced using the Bangor bar, and also with the proper heights of the Bangor bars can further reduce low back strains. So based upon this, I'm not going to go to the limitations of future directions due to the interest of time, but based upon what we found, we have, made a outreach materials and to disseminate this to the participants and also commercial fishing community in Washington, Oregon, and California. And when they receive these, the outreach materials presented on the left side, uh, a few fishermen and local fabricators actually reached out to us, asked for drawings. So we actually created this, in 3D AutoCAD to so that they can actually recreate these structures for them for their vessels. And those are some the examples showing that our research didn't stay in the lab, but also actually reached out to the actual commercial fishing communities and then translate into the practices. And also another fascinating study that we recently completed, and still this is a pilot project, but still we are expanding this to the real project. We are Our targeted N is 20, but I think I'm presenting based upon our preliminary study with sample size of 6. But we have completed the 16 measurements so far, and we plan to complete up to 25 subjects. So basically, this is also another example of fisherman-led interventions. So we have a brilliant commercial fisherman who actually professionally, scalloping, chunking the scallops, whose name is Farrell Davis, and he has a brilliant idea of modifying these chunking knives to reduce those wrist and hand strains among those scallopers. So basically, the group of those scalpers are really exposed to various hazards, not only by mechanics but also biotoxins and some other cuts and the traumatic injuries. But there is no really studies looking at looking at the interventions can mitigate these risks. So this is the commercial fishermen who actually part of this study. We wanted to use the wearable sensors to objectively evaluate the muscular load associated with the shocking the scallops and evaluate, that tool design to reduce the muscular loading associated with the scallop shunking here. So, so this is actual video footage. This is a actual commercial fisherman who actually doing the scalloping, and we use this wearable electromyography sensors that actually can be paired with the smartphone and any smartphones or iPad. And this is very the fascinating tool because it's only $150 per sensor. So we bought several of them and have them to use it. It requires minimal the training, and we train these commercial fishermen. They can actually, collect this data, and as you can see, as this person is shunking, we can see the real-time data, and then we can post the process, and then some of the data I'll be presenting on this the next slide. So basically, the outcome measure was muscle activities, and we did conventional signal processing on the EMG, but I'm not going to go into details. But this is a highlight of what we found. So shunking scallops requires the really high level of forearm muscle activities. As you can see, compared to their maximum voluntary contraction level, basically it's that they're like equivalent to their maximum activity levels they can exert. They almost use somewhere between 20 to 40% of their maximum capacity, and compared to conventional manual material handling requires only around the 20%. So basically this is showing how intensive the shocking task is. And this is and the blue bar showing the extensor muscles, which is responsible for the wrist extension and finger extensions, and then the orange color showing the flexor muscles, which is flexing the fingers and flexing their wrist motions. So basically, shunking clubs is a very fatiguing process. But we also, compare between the stock knife versus a modified knife by the commercial fishermen. So as you can see, especially if we look at these flexor muscles on the left side, the star or asterisks in the middle of the graphs representing the statistical significance, but let's not focusing on statistical significance because we have only, n equals to 6. But basically, and as you can see, this modified handle knife has, showed the lower muscle activities as compared to the stock knife, which is showing the potential benefit of modified knives. So the Farrell, who's leading this project as a commercial fisherman, is actually, 3D scanned all the existing modified knives by those commercial fishermen. He's creating the library of these to, develop a 3D printed knife handles so that he is evaluating this in the next phase. And this is another example of using wearable sensors and partnered with the commercial fishermen, and they use the commercial fisherman-led interventions to evaluate in the both in the lab and field settings. And we have been doing the similar studies with the various occupations, and this is a very similar project we did with the commercial fishermen that I presented a few slides ago, and we are expanding this with the first year workers and showing very similar results. And since we already showed some of the results with the commercial fishermen, I'm not going to read these graphs, but I'm happy to show this slide through Greek and through the centers. And if you're interested in, you can look at this slide later on. So just moving on to, the wearables and AIs, and you have seen, comparable wearable sensors that we used for commercial fishing and forestry, and also different EMG sensors for, scalpers. But those wearable sensors are great because we can, you know, have the fishermen to wear and let them go work in the field during their regular shifts. But always putting those sensors is always cumbersome, and also we have to record them. We need to do the skin preparations and some other things, and still less invasive, still it's intrusive. However, using like simple cameras, even we can use smartphones or your phone or worker's phone. We can do ergonomic assessment instead of using those wearables. We can just use smartphones, and this is one of the examples that we used, excuse me, we used a smartphone video footage to do the 3D biomechanical model using this. And conventionally, we have to use the 3D motion captures in the lab where we have anywhere between 8 to 20 cameras with a first place with this, which setup can be easily 100 grand in terms of cost. But just using your video, the video you captured from your smartphone can actually do similar things, still provide somewhere between like 85 to 90% accuracy, and which does not require any additional lab grade scientific instrumentations. And this will, really open up a new opportunities for us to do those ergonomic assessment differently among those agricultural workers, and even we can autonomize and with these risk assessments. And also using these wearables, and we talked about the heat exposures earlier, and we partnered with my collaborators in Binghamton University in New York. We developed a nano printed a skin patch that you can see from the left top corner, and this actually collect the sweat samples, and then detects certain chemicals that from your sweat to see if there is any heat related stresses, and also if there is any lactic acid presence or any oxidative stresses related hormones that detected as a result of strenuous work in the field. So using those wearable skin patch, we can actually provide the real-time feedback to the workers who may not necessarily know anything related to heat exposures or heat related the illnesses, especially among the immigrant workers, which are who are common in the agriculture. And using this sensor-based network, we can actually provide the real-time feedback to the workers to do more prognostic, work, and also provide the more proactive, intervention opportunities. So this is, still ongoing study, but I'm just showcasing what we are doing with agriculture workers and others. But this is really fascinating because we knew that this is possible, and the left to the lower corner is something that we developed several years ago based upon the wearable computers and Raspberry and wearable sensors. Back then we still were limited with the computing power and also limited storage in the memories. But with this new like AI computing powers and improved the connectivities through various means, and we could open up these opportunities to further improve and to improve this vitality of this sensor network to do more real-time proactive risk assessment and feedback systems. And also, the falls are particularly concerning among those, agriculture heavy equipment operators. And also, this is very common, the injuries among the elderly workers in any industries. And we have been using computer vision and wearable sensors to detect the fall risks and provide the real-time feedback about their fall injury risks using various the machine learning algorithms. And those are just some of the highlights of what we've been doing. The reason I'm just doing the quickly going overview of these is just to show you what we can do and for you, and if you're interested in working with us, and also if you have any really fascinating ideas and the some of these work can be beneficial to you, and then I would like to highlight that me and my collaborators will be happy to work with you to to introduce some of these approaches that we have been doing. And for the next 10, 15 minutes or so, I would like to also show some of the exoskeleton research that we have been doing. And we have done a lot of exoskeleton research in various occupations, ranging from agriculture, logging, commercial fishing, mining, healthcare, and construction workers. And some of them I will be just showing is related to a little bit of agriculture, especially on logging. And we all know that manual timber felling is still prevalent and required, especially in the Pacific Northwest, where the terrain is very stiff, where these machines cannot access. So however, these manual timber felling and timber fellers are exposed to various, hazards. And we have, as I showed you earlier, using wearable sensors, we found that their low back strain is, substantial during the manual timber felling. And we know that, back support exoskeletons can actually alleviate those strains on the we that's have been documented in various occupations in the construction, warehousing, manufacturing, and so forth. So we wanted to see if it is feasible for us to use these exoskeletons in commercial manual timber felling tasks. So basically, but however, we didn't want to, evaluate this in the field settings without knowing what are the benefits and risks associated with exoskeleton use. So we evaluated this, the both benefits of and the risks of using the exoskeletons in the lab-based settings while we are simulating their cutting tasks, tree cutting task, and these were the four exoskeleton condition. Again, the no exoskeleton condition served as a control conditions in conventional tree cutting, and then we had a three different exoskeletons. So just for your information, I listed some of the features and their specs, but please don't pay attention to it for now. But to just for we have various exoskeleton types and conditions so that we can compare and contrast among those conditions. So basically, this is cutting postures for three different common tree cutting heights, low and medium and high, to represent what they are actually doing. And the cutting height were determined based upon the professional timber fellers' feedback by inviting them to the lab as we did with the commercial fishing projects. So as we did with the commercial fishing, we used various bioinstrumentations that commonly used in ergonomics and biomechanics research. I'm not going to go into the details, but we followed all, the recommended signal processing and they used the summary measures. So, this study took anywhere between 3 to 4 hours. But basically, after we fit those exoskeletons, have each individual go through 4 different exoskeleton conditions with adequate break in between, and to evaluate the efficacy of the exoskeletons. And this is just a brief summary of what we found. And so especially, in the middle cutting height, so this is showing the low cutting height, middle cutting height, and high cutting height. As you remember, if we go back to the slide back again, and as you can see for the low and high cutting height, and torso flexion was relatively smaller because, for the low level, they have to kneel to cut, and high level, they need to stand upright. But exoskeleton supporting mechanisms only get activated at a certain range of the torso flexion. So we somehow expected that we are not going to see the low and high level, see the benefit at the low and high level. Then why we evaluate that at level? That was because we wanted to see, while we provide the maximum benefit of the exoskeletons and medium height, we also wanted to make sure that at the low and high levels that the exoskeleton did not introduce any adverse effects on the low back or other muscle activities. So that being said, if we look at this middle, so when they compared to compared to no exoskeleton condition, which is a lighter gray bar, having these rigid exoskeletons, which is shaded in the gray, showed the lower most activities as compared to no exoskeleton condition. But somehow the soft exoskeleton, which is apex, which is based on the fabric elastic band, show no effects on it. So this is showing that the rigid exoskeletons may have a potential to reduce the low back muscle activities, but not the soft exoskeletons. And this is showing the upper back muscle activities, a pretty consistent trend. And we saw greater effects from the rigid exos, but not on the soft exoskeletons. And we are we are also evaluating exoskeletons in the commercial fishing because, as I mentioned earlier, these passive exoskeletons are known to reduce the physical, strain, especially in the low back and shoulders, especially for the low back exoskeletons on the shoulders. However, there are some, potential adverse effects as well. But we wanted to, before we evaluate this in the field-based settings, we wanted to see if the exoskeletons can be also feasible in the commercial fishing, very similar to what I just presented in the logging. So basically, this is basically similar to what we have for different exoskeletons, and this is ongoing. We just completed data collection. We don't have the data to show yet, but our team is actively processing all the data at this point. But hopefully, maybe sometime near future at the conference, or if I come back for the webinar, hopefully I could share some of those findings. And also we plan to disseminate through various channels here. And also the exoskeleton is great, but at the same time, most of them are evaluating is commercially available, but they are not necessarily designed to specifically fit to certain tasks. For example, all the exoskeleton that we exoskeletons that we have evaluated were not designed for either commercial logging or commercial fishing. So, we currently working on, the computational biomechanics to identify what would be reasonable or if there is exists the optimal level of the supporting torque for certain tasks to uh, better customize these exoskeletons to better fit to the certain tasks in the agriculture. So that's what we have been doing. And this is one of the like study that we've done. So like using really complex 3D biomechanical model and skeletal models, we superimposed AutoCAD created the exoskeletons into this model to see how different or various supporting torque from the exoskeletons affects the low back and other body biomechanics. And basically, this is the right side that's showing the supporting torque profiles from the flexion and extension. Yeah. So, but basically, you don't have to go much details. But the bottom line is we wanted to go from the lighter support to heavier supports to see if there are any trade-off between the benefit and risks. For example, having the greater support will better alleviate your low back strains, but at the same time, it can also create a lot of contact stresses where the exoskeletons contacts the body parts, right? So, and also on it will also create a lot of movement impedance as well. So just by changing this, we would like to find sort of optimal range of the supporting torques. And this is what we find as a preliminary analysis. Basically, this is the low back shear force. So basically, as if this bar graphs is a little bit difficult to digest, just for it's better to have larger green space than the red space in each bar. So in the no support conditions or no exoskeleton conditions, we have a lot greater red regions than green regions. But as we increase this supporting level from 40% to 100% of that, the supporting torque, then this shear force actually, substantial decrease over time. So this is how you can read these graphs. But this graph show more than this, but just due to the interest of time, you can just, simply intuitively think, okay, so green space is better. So, greater support was good for reducing shear force. However, as that support torque increases, as you can see, the contact force on the chest on the left and the thigh on the right side increases. What that is like we also measure the contact force on the chest where they have the vast that actually harness the exoskeletons with the human body, and also it has a thigh strap that's the another part of that interface between the exoskeleton and the human body. So the greater contact stress means that greater discomfort or pain. So think about like if you have if you are resting your wrist on the edge of the table, if you just press your wrist against the table hard, it will increase the contact force. Then you will feel the pinch and then feel discomfort. You can interpret these bar graphs like that. So as we increase the supporting torque, we were able to reduce the shear force on the low back, but at the same time it came at the expense of increased contact forces. So those are just all like snapshot of what we've been doing in terms of wearables and the exoskeletons, particularly in the agriculture industries. So take home message here, we all know that agriculture industries, even though the folks in this room have tremendous job and putting a lot of efforts to have improved worker safety and health in agriculture, but still, due to the inevitable natures and exposures that we are facing in agriculture, this industry remain dangerous. And also there are emerging challenges as well. However, these new technologies, some of them are presented today, may open up new doors to improve this, the worker safety and health in our the field. And of course, more research is needed to advance this field. I welcome you to be part of this, and I'm really looking forward to work with you if you are interested in working together. So I think with that, I will just close this. I think this will give us ample time for the discussions and the questions.
Great.
Thank
Thank
you
you
so
so
much for
much.
your
Thank you so
time.
much, Jay. Appreciate that. I'm going to go ahead and put in the chat for everyone. This is the evaluation link. When we're finished with the webinar, please go to that link. We'll also have time to share some more information with you as well. Please go ahead and put in the Q&A any questions or comments that you have. We do have one question here. It says, thanks for the presentation. Where are you conducting the research on the knives for scalloping?
So that's a good question. It's being done in New Bedford in Massachusetts, and all the measurement is being done on the vessels.
Great, thank you. Well, before anyone else puts any more comments or questions in there, Jay, I mean, you've mentioned several times during your presentation, the potential of having collaborations or people who are interested in working with you in the future. What would they need to do? How would they contact you? I do have your email address up there, j.kim@tamu.edu. Is there
Mhm.
anything other ways that they might be able to work with you, collaborate with you, or contact with you about possible work in the future?
Sure, yeah. Email is, I think email would be the most convenient way of communicating, and we can, we can set up the Zoom meeting afterwards. But I think that will be, the single most effective channel of communications. But at the same time, we have a website where you can look for more information about what we're doing, and not only limited to agriculture, but yeah, so I think feel free to reach out to me if via email, and also if somebody prefers to talk over the phone, I'm happy to share my the phone number as well.
Great. Um, let's see. I think that may be everything at this point. Jay, again, thank you so much for your time. This is really exciting, groundbreaking work here, looking at how technology can be used to enhance and improve the working environment of fisheries, agriculture, mining, and forestry, and then other related industries as well. So again, here is the link to the evaluation. You'll also be receiving that link in an email from us for attending today's webinar. We thank you so much. The next webinar for the Southeastern Coastal Center for Agricultural Health and Safety will be in early September, and we'll be focusing on mental health. So again, thank you all for joining us today. Thank you, Dr. Kim, for being our presenter as well. And we hope to see you and get your questions and comments at the next webinar coming up in less than a month. Thank you so much.
Thank you. Thank you for having me.